I'm Andrew Cooper. Probably most of you know me. For those who don't, I been working at Citrix for 15 years now. Really not quite sure where the time has gone. In upstream Xen, I'm an x86 maintainer on the security team. Do quite a lot of work, mostly x86 related, but also general hypervisor. Today, I was going to talk to you about flexible event and return delivery. So what is fast return and event delivery? Because it turns out it's had two names, both of them are Fred. Originally, Intel was working on this as a performance optimization. It just so happened that they were working on it at the same time that the world went through the Spectrum meltdown crisis and suddenly got a whole bunch of hardware people and a bunch of software people in the room together, and some discussions started happening. Overall, Fred is probably one of the biggest overhauls in x86 in a generation. At a previous Xen Summit, which it turns out was actually 2021, so quite a long time ago now, I presented on stack switching problems specifically. At that point, it was just after the first draft of this. Well, I say the first draft, it was 0.5 of the Fred specification being published. So I presented the two options at that point. We're now up to version 9, and it is appearing in hardware later this year. I believe the first one to come to market will be in Intel Panther Lake, and it'll be coming in server CPUs shortly thereafter. The way x86 CPUs deal with interrupts and exceptions has fundamentally not changed since the 286 processor, even the original 8086 to a certain extent. You have tables in memory. One of them is called the interrupt descriptor table, and it's got 256 entries in it. It references a code selector, which you look up in a different table, the global descriptor table or the interrupt descriptor table. And you may need to also get a stack pointer, which comes out of the task state segment. And it also includes the main entry point to jump to. The local and global descriptor tables contain a bunch of segments and various other descriptions. They're a little bit more complicated. They also contain a thing called call gates that no one uses because they are not binary compatible between Intel and AMD CPUs. In some corner cases, no one uses them, but they are relevant later. And there's also the task state segment that contains various bits that are lost to the history of x86, and also the stack pointers on entry. And the big performance problem here is that you have at least 3 or 4 memory reads to perform on every interrupt, every exception, a whole bunch of cross-checking that needs to happen. The code segments and data segments in the global descriptor table have access bits that need setting if they weren't previously set, and that must be done atomically. All of this is really slow. It's complicated, and it needs auditing every single time because one cycle later, someone may have written into memory, changed some of the tables. This made sense back in the 286 processor where you couldn't fit even another single transistor into the silicon and everything had to be in memory. But very quickly it became problematic. Now, this, don't worry too much about it. This is roughly what it looks like in 64-bit systems. In 32-bit, it's even more complicated because the code segments can have a non-zero base. So they get joined back up into the base pointer for the ring 0 code. And the task state segment also had stack segment selectors in them as well. To fast forward to the end of the presentation a little bit, this is how much more simple it looks like in Fred. Obviously appreciate that there's far less looking up, and we'll go back to some of the problems in the middle. There are a number of other problems. So more than simply the memory lookup and the cross checks that happen, there's a bunch of things that are not completely great. When you get an interrupt, when you get an exception, the processor doesn't tell you what it was. The only way you can figure that out is which of the 256 handlers started running, which means you can't point any two of them together because then you can't distinguish which was the incoming vector. As a result, a whole bunch of code, you have to have 256 entry points, and genuinely what happens is every single one of them puts a number on the stack and jumps to a common handler. So you have to write 256 that have a couple of instructions and then join back together into a common code path, because that's how everything works. The other problem is that the interrupts and the exceptions overlap. This is a consequence of the development through the 286 into the 386 processor. So some exceptions in the range 15 through 31 overlap with interrupts in that particular range. And those that have an error code have a different layout on the stack. It's one word different on the stack. There was a paper done attacking Xen, actually, in 2011, I believe. It's from Invisible Things Labs, who are the company behind CubesOS. And it managed to get a privilege escalation into the Xen hypervisor by confusing an alignment check exception with an interrupt. And that was to do with the different layout on the stack and that not working safely. The other thing is, in 64-bit, most code has to switch GS base pointer to get to the per CPU pointer. Xen does not need to do this, but it's relevant to the design of Fred because literally every other operating system does. And therefore, Intel decided to go with the common way of doing it. It was very quickly discovered that the interrupt descriptor table is not a great way of doing system calls. So in the AMD K5 and the Pentium 2, you had Intel and AMD both inventing their own way of doing faster system calls. So even back in the late 90s, early 2000s, it was known that there were performance problems with the IDT way of doing things. Generally speaking, the syscalls, they were configured in model-specific registers. They deliberately avoided the tables in memory. And they also got rid of a lot of the configurability because no one really used the flexibility available in the architecture. Both of them had problems. Syscall and sysret was the ones that AMD did. It doesn't switch the stack, and that leads to a whole bunch of privilege escalation bugs. It uses two general purpose registers, which is fine if you're expecting that to work, expecting that to be used, but it means you can't use it to return from an interrupt. You can't use it to, you can only return to a specific point that was doing a system call, which means you can't use the faster way of returning to user space in the general case where you did something completely behind the back of user space, such as handling an interrupt. Syscall and sysret, well, syscall forgets the outgoing code segment, stack segment, and whether you were in user space or kernel space of the interrupted context. If you think that's bad, Intel managed to do worse. They lose the code segment, the instruction pointer, the stack segment, and the stack pointer of the interrupted context. I genuinely don't understand how they thought that was a good idea. And they also don't sanitize the flags, which is great. You can single step your way into the operating system, and any OS that doesn't deal with this has a privilege escalation problem. The point here is that they were fast, but they were overly fast. They were trying to get down to a couple of cycles on processors a long time ago, and they cut out bits and pieces that turned out to have been a very unwise move later on. Fred tries to go somewhere in between these. First of all, it deals with system calls in exactly the same way as it deals with interrupts and exceptions. The original system calls were added as a bodge on the side because the customers were demanding more performance, but it was not architected into the original design of how x86 system calls worked. All the configuration is in model-specific registers, which as a practical consequence means that the interrupt descriptor table and task state segment are no longer used, which is great. It means we can avoid allocating them. It's fantastic. The hardware also guarantees to enter on a good stack and with the right GS base. Critically, there are the world's supply of security vulnerabilities where you either get one too many or one too few swaps of GS, or whether you haven't quite set up the stack correctly before you start spilling other registers. So there's 15 or 20 fun ways of getting privilege escalation into a kernel that doesn't know all the ways in which x86 is broken. Fred also pushes a full Fred frame. I've got a diagram of that later. Importantly, it means you always get all the metadata. We no longer lose any state. And because we have all the state of the outgoing context, we can return to it transparently. We're no longer in a position where we have to use a slower way of returning just because it's an interrupt. Fred does disable a few legacy features. For anyone that knows the deep history of x86, rings 1 and 2 are actually no longer usable. They were basically on life support from the 386 processor, but we have finally killed it 30 years later. It also gets rid of the ability to use 32-bit mode operating systems. No one really cares about that these days as well. It simplified a few bits. A whole bunch of instructions now are disabled. These are the instructions that would violate the principle higher up to always enter on a good stack and on the correct base pointer. The final one is disallowing the use of call gates. Now, I like this bit specifically because I suggested it and Intel said yes, but critically, it makes a security improvement. Previously, it was the case that the entry points were in memory. So if you get any kind of exploit chain where you've got a partial write primitive and you can edit the IDT or the GDT, you can hook execution and escalate privilege into the kernel. That's obviously a more complicated attack vector than some of the other ones, but by getting rid of call gates and also getting rid of the IDT, we remove any trace of there being entry points registered in memory, which is actually a huge security improvement over previous cases. Now, even if someone has an ability to write memory, they can't change the configuration of how do you handle interrupts, how do you handle exceptions. Obviously, they can probably subvert some other logic, but that's even harder than before. So it's still a useful barrier to have in place. Yeah, it's kind of readable. I would ask to do a poll. Does anyone recognize what the blue stuff is? Yeah. Anyone? Yeah. Oh, yes, but Jan, you're an x86 maintainer. I'd be concerned if you didn't recognize it. So the blue stuff here is what current IDT handling looks like. So that's what CPUs do today. It's what they've done basically since the 286 came along. This is the 64-bit format of it. That's fine. The well, it's supposed to be orange, but frankly, it looks more yellow, are the new bits of state that we get from Fred. Fred puts rather more metadata onto the stack, and that is specifically useful for a number of things. And also the green bits and pieces are currently reserved. I've been informed that I must say they are currently reserved by some of the architects that did it. There may or may not be plans to use some of them for new features. Above the code segment, so these bits here, we have the stack level and the wait for end branch. Both stack level is new in the Fred architecture. Wait for end branch is fixing a previous bug that existed in the architecture. There's a feature called control flow enforcement technology, and it had a very fun bug whereby if you had an interrupt on one specific cycle, you'd fail to do enforcement of the security policy that you had compiled your code with. And that was because this particular piece of state just got lost when doing an interrupt. So it's been put back on the stack. Above the stack selector, you've got various other bits, STI, software in NMI. That's more state. That kind of, each of them have complicated behaviors, but they're bits that are presented to you by hardware and that also take effect when you return in the context. Above that, you've got even more information. You've got the vector, you've got the type, you've got the instruction length. All of that is metadata that previously we either didn't have at all and had to figure out, well, all of it we had to figure out ourselves. Some of it we were capable of figuring out, and some we genuinely were not capable of figuring out. So all of this metadata is now provided by us, provided for us, I should say. It is a uniform layout. Importantly, Fred guarantees to always write the same stack layout, which means you can no longer get confusion as to whether you have an error code or not. The stack layout is the same. Which is a useful behavior. Remember earlier where I said there were 256 entry points? We now have 2 of them, literally 2. One of them is the entry from ring 3 and one's the entry from ring 0. It turns out that in operating systems, it is what you need to do on entry into the kernel depends far more about what you interrupted, not why you were interrupted. So which context? There's a lot you have to do differently if you're interrupting from user space than if you're interrupting from the kernel. Similarly, on the exit paths as well, there's you tend to do different things. So return from the kernel back to itself generally does nothing special. Return to user space has a whole bunch of checking that it needs to do simply to continue to use user space in the way that people expect. We get 2 new instructions, the ERET-U, ERET-S. These are kind of synonyms to IRET for those of you who know what it is, but it behaves in a rather more sane way. We get 4 stack levels because even the previous ones, I mean, the interrupt stack tables in 64-bit were kind of nasty to use. In reality, we only use 3 of them, and frankly, we could probably get away with 2. You need a separate stack to handle double faults, just so you can print some logging out to the console before you finally die. I put machine check on there as well. It's debatable what to do. But because all the other stack handling works nicely, we are no longer in a position where we have to handle NMIs separately and debug exceptions separately. A lot of care has been taken to allow the exceptions to nest correctly. My talk back in 2021 was about all the ways in which this goes wrong in the architecture at the moment. You can end up having logically left a handler but are still using the stack, and you can get corruption based on that because of the way things evolved in the architecture. Now it's been redone from scratch, and the ERET-U and ERET-S instructions take care to atomically leave a stack and do the other bits and pieces associated with it. A few more are lower down the slide. A big thing is the instruction length being exposed to software. x86, famously a variable length instruction set. So when you get a trap that happens after the instruction, sometimes you need to go back to the start of the instruction. Previously, we had no way of doing that. You cannot look backwards through the instruction stream and find the start of the instruction. It is not possible in x86, and yet we needed to do that in a couple of cases, and there are grim hacks for making that happen. But now the hardware tells us how long the instruction was. Because some of the metadata in the IDT went away, we now need to do a few more checks than we did before. For example, hardware doesn't do DPL checking, but that's fine because no one really used the flexibility that was available there. We need it just to maintain the same behavior on VMs that can't see it, but that's easy enough. Another complicated problem that was not discovered until quite late, if you take page fault has a secondary status report in CR2, Control Register 2. Similarly, debug exceptions in the debug status register, DR6. If you take a nested exception before you have read those out of hardware, you clobber it in hardware, return back to the old context, and it pulls the wrong status or the sequentially wrong status register out. Nowadays, that's presented on the stack. So even if you take 3 page faults in a row, each of them gets the correct status information with them. That matters quite a lot more for Linux. Linux does some really crazy things with page faults because they're constantly touching user memory in weird environments. Xen, we think it's not a problem, but we decided to go and fix a bug in that space anyway because we weren't sufficiently certain it was not a problem. And a whole bunch, I alluded to this earlier, wait for end branch, blocked by STI, single step, and the NMI latch are now pieces of state that did genuinely exist in the processor previously that we can now actually restore correctly and provide better behavior to the user space that did them. Previously, we'd just have to ignore it, and things may go wrong. The single step is rather fun. You can spot when interrupts happen if you single step yourself and notice where you do not get single step exceptions. And up until Fred, there was nothing the operating system could do to correct that behavior. It was an information leak into user space. This came with some changes in Xen. I say some changes. I think I've already committed about 60 patches or so. The remainder of the work is still 24 patches left. I mean, most of it's now reviewed. I need to do one more series and post it. The big thing was the split of a type. For reasons of some of the past developers not necessarily being as diligent as we'd like, there was this type used internally within Xen that was also presented externally in the public interface and used in the hypercalls to start a vCPU and set its state. And the problem is that the one that exists in public had the virtual x86 modes segment selectors in them, which ceased being relevant in Xen in 2011 when we deleted 32-bit support, but it's still around. In Fred, that area of the stack is reused for something else, is reused for the event data. So we're genuinely in a position where we have a type in the public ABI that cannot change and also must retain its current name. And we also have a type inside Xen that must retain its name because it's common across architectures. There's some dodgy stuff. Please don't go and look how I did it. That was nasty. All the dirty laundry is actually in the public header files for that. One thing that I was not expecting, we actually had to get rather stricter about how we handle reserved bits in the hypercall. So the get set domain state APIs. One of the things, so in x86 there are two common bits to find. One is in the flags register, another is in DR7, which are sticky 1 bits. So they're previously you could write either value to them and you'd always read back 1. It's very useful for distinguishing a real dump of registers versus a block of zeroed memory. But the IRET instruction didn't care about this. It would just accept the 0, ignore it, and give you 1 back when you looked at it. ERET-U and ERET-S do care about this. I found this out the hard way when running the code. So we have had to make a few subtle changes. I mean, technically they are ABI changes. We've deemed them acceptable to make. But yes, that was an unexpected discovery along the way. The other thing we have to do is rework all the GS-base accesses. Because all other operating systems use GS in the way that AMD wanted you to use it back when they did the 64-bit architecture, Fred automatically swaps the GS base for you, which is correct for everyone else in the world. Xen is special. Xen doesn't use GS base because the guest kernel and guest user do use it. As a result, in Xen, which GS base is which depends on whether you're logically in guest user mode or guest kernel mode, or context at least. Under Fred, they're the opposite way around because hardware automatically switched it for us on the way into the hypervisor. I have done my best to comment this in the code. I don't like the result, but it could be worse. There is actually one place where we need to emulate a swap GS instruction now because we're not allowed to execute it ourselves, which in turn required going and doing some rather nasty rework of the MSR logic. It's worth saying that the Fred architecture comes with a new instruction, the load kernel GS base instruction, which, as it turns out, Xen does not need, which is excellent because it avoids a nasty binutils problem. Overall, the status of this, I have been developing it in Intel Cymix. This simulator, it's available online. I have not yet had access to real hardware. We've agreed to merge it into Xen 421. It's going to go in as experimental because even I'm not quite brave enough to put that in as supported until I've actually booted it on some real hardware. As I said, there's a lot of prep work that's gone in over the 421 release. There's the final bits to review and merge. They're mostly ready now. I will get back to it when we're not in a conference. Hoping to make it fully supported in 422 after we've got some real hardware. As I said, the hardware is going to be on the market later this year, so 422 seems reasonable. Obviously, with everything, there's future work. This, at the moment, is only getting Xen able to use it. At some point, we're going to want to get guests able to use it as well. That hopefully shouldn't be too hard. It's reasonably nice. Yes, Alejandro here is sniggering in the corner. The other thing that we get is a feature called NMI source reporting. That's quite interesting. Previously, non-maskable interrupts in the architecture, we use them for everything. We use them for the watchdog, we use them for performance, use them for fatal errors out of the system, and you just get, there was an NMI. No further information with it whatsoever. Also, NMIs are edge triggered. They can merge whilst they're waiting to be serviced. So every time you get an NMI, you must check every source of NMI that you know. And if you do not find one, you've got to figure out what to do with an unknown NMI, because usually if you don't know what generated it, it will be a random piece of equipment in the motherboard, probably hitting a PCI serious error or whatever. One of the things that you do get now in Fred, particularly now that NMI is distinguished from others, is that we have an ability to use vectors with NMIs, which means that you can program the different NMI sources using a different vector, and then hardware will tell you which of the vectors turned up. It may tell you that multiple turned up, because NMIs can still merge, but you basically get a bitmap saying this interrupt had these 3 sources or whatever, which is excellent, but that's also work for the future. And with that, I think we're getting...
It's a sign.
Okay, it's a sign. Right, any questions?
Let me get the microphone over
yes.
there.
I can do my own mic running, I guess. Yeah, that's good.
Can Xen emulate Fred for the guest without hardware support?
Depends what you mean by emulate. For a PV guest, yes. In fact, I have a crazy idea to do this anyway, because it will actually delete a bunch of the PVOps stuff out of Linux that the x86 maintainers in Linux hate. For HVM guests, no. With HVM guests, we do our best not to intercept them in the first place, and therefore if hardware is not capable, it's not capable of doing that.
One of the rather annoying features of the IRED instruction or IRED queue is the fact that it can fault itself. Yes. And screw up its own stack layout.
No, it behaves like everything else that faults.
Yes, and then you have to pick up the pieces.
Yes. ERECU is exactly the same, yes.
It's exactly the same, that there was nothing to...
Well, so ERECU can fault. Right. You are taking some state from user space, or as specified by a hypercall, or that there are illegal states. You can have non-canonical pointers. You can have various metadata attributes that are wrong. So the instructions can fault.
So what is the semantic when, say, you want to return to your user space address that doesn't exist? You get a page fault. Do you get another Fred frame on top?
Yes.
And okay, but not a partial frame, right? Not something idiotic like that.
No, you get a full frame. So what there were bits and pieces in there I definitely brushed over, because Fred is a long, complicated spec. One of the things it does is always align to 64 bytes first, because of working around other bugs that exist in virtualized environments. As a result, you actually get quite a big difference between the Fred frame of the exception and the original frame you were trying to use to return to user space.
Okay. Well, but still, there should be no need to do a fix-up and pull back the frame to where it was. So that's a definite improvement on the current state of affairs.
There is fix-up required. The way you do the fix-up is different. And there's one patch in particular with a lot of comments trying to explain that.
Okay, I'll have to have a look at that. Cheers.
I was just wondering, how did you enable Xen to determine which mode of operation is available for the platform it starts up on?
So the platform, okay, so Fred is a bit in the control register. You must turn it on. It is bit 32 in control register 4, which is problematic because it's the first bit above regular 32-bit operations. It is deliberately there so you can only enable Fred when you're already in 64-bit mode. And also what you find out is all the paths in the hypervisor where we were doing 32-bit logic for updating the CR4, which had a side effect of truncating the Fred bit out. That definitely caused a number of crashes. The reality is, even on Fred-capable hardware, the old mechanisms still work for backwards compatibility. In practice, we can't turn it on as early in boot as I would like. We need to parse the command line. We need to figure out whether we're using set or not. We need to figure out whether we're using PV-shim. So right now, what we do is we set up some very basic exception handling so we can just print out a panic message, and then slightly later on boot, we look at a number of information sources and decide whether to use Fred or not. At the moment, it's off by default, and there's a command line to turn it on. That will be changing. I have already written the patch to change it. I just need to do all the other bug fixes in the meantime to make that happen.
I did one follow-up. So now we have 3 different ways of handling this in Xen. There's AMD's, Intel's, and Fred. And the implementation, I mean, what does it look like, right?
There's only one Fred spec.
No, I mean, you have to support ones that don't support Fred.
Yes. So there's all processors in the world at the moment, and we have to continue supporting that. And starting from Q4, there will be processors that support Fred. And the 60 or so patches to make that work, a lot of that was rearranging some of the setup and some of the stack layout so it was broadly compatible between the two. Obviously, Fred has a reasonable amount of backwards compatibility to the older IDT way of doing stuff. So the layout on the stack, okay, you've got to tweak the exact entry point on the stack, but by most of the data there, Fred just gives you extra data you didn't previously have, or a guarantee of data where previously it was variable. So I had to do some changes to which stacks we do where. I had to do some changes to how we set up trap handling, but the actual changes to the exception handlers were very small in the grand scheme of things.